So this is the second part of 1.5, dependent events. Okay, and the goal here is to use conditional probability to solve problems involving dependent events. So what's a dependent event compared to an independent event? Now, remember from yesterday or the last lesson, independent events, there are two different kinds of events that don't affect each other. The probability of one thing doesn't affect the other thing. For example, rolling a dice doesn't affect the probability of flipping a heads or tail on a coin. But dependent events, well, if the occurrence of one event influences the probability of another event, then we say the events are dependent. Okay, so we define this new thing, a conditional probability. So the conditional probability of a second event, which we usually label B, looks like this. So this says the probability of an event B, the second event, given that event A has already occurred. So this is what this notation means. So it is the probability that B will occur given that A has already occurred. And the sample space for the second event is reduced by the first event. So if something happens in the first event, you just take it away. You take away that object from the second event. Okay, so this is the product rule for dependent events, and it says that the probability of a dependent events occurring is the probability of event A and B occurring is equal to the probability of A times the probability of B given that A has already occurred. Or if we rearrange the formula, we can say that the probability of B given A is equal to the probability of A and B divided by the probability of A. Okay, so this idea, we'll take this idea and this formula and try and apply it to some examples to show you what this means. So the first example. 2 red checkers and 2 black checkers are placed into a bag. What is the probability that a red checker is randomly chosen, followed by a second red checker, assuming the first checker drawn is not replaced? And this idea of not replacing something, that is really key here in dependent probability. And the reason why is because it changes how the second event the outcomes for the second event. Okay, so let me just go through the motions of the formula here. So let's first define our events. So our event, we're going to say let A be drawing the first red. So this is drawing the first red checker. Okay, and so if you draw the first red checker, inside your bag you only have 2 black checkers and only 1 red checker left. So when you're doing the second drawing, you've changed the event. You've changed the event. So let B be the second red checker. But the probability of getting the second red checker is different than the probability of getting the first red checker because we never put back that first red checker back into the bag. So things have changed. So the probability of event A, we can say, well, there's 2 red checkers out of 4 in total. And that's fine. And if we reduce that into lowest terms, it's going to be 1/2. So you have a 50-50 chance of drawing a red checker. But the second event, what happens when you draw your second checker? So the probability of drawing a red, given that you've already drawn 1 red, is going to equal to, well, there are only 3 checkers left in the bag because we never replaced them. And there is 1 red checker in the bag because we never replaced the first one. So there's only 1 red checker out of 3 total checkers left in the bag. So this is what is meant by not replacing the first checker. And so this creates this dependency. This event depends on the first event actually happening. Okay. So let's answer the question. So what is the probability that a red checker is randomly chosen followed by a second red checker? So we want the probability of both A and B happening. Okay, so probably of drawing the first checker is red and the second checker is the red as well. So that's going to equal the probability of the first event, A, times the probability of the second event, given that the first event occurred. Okay, so these events are dependent on each other. If you had replaced the checker back into the bag, in the second event, it's as if the first event never happened, and the second event can be calculated, the probability can be calculated just like the first one. So the second event would have just been the same probability, 50-50 chance of drawing a red checker. But the fact that you're not replacing that red checker changes things. So here we have 1 over 2 times 1 over 3, which is 1 over 6, okay, or 16.7% chance. So we're going to say here, therefore, there is a 16.7% chance that both red checkers will be withdrawn. Both red checkers will be drawn. Okay, and compare that to what if you made a replacement? Well, if you made the replacement, you put the red checker back, well, it's a 50-50 chance every time, so it'll be just 50% times 50%, which will be a higher percentage, 25%, compared to the 16.7. Because when you remove one red checker, well, then all of a sudden the likelihood of you drawing a red checker again has all of a sudden gone down for the second event. So that's what is happening here. Okay, so let's look at the second example here. So Gabriella's computer sometimes crashes while she's using her email program Outtake. When Outtake hangs or stops or freezes, you can say, she's usually able to close Outtake without a system crash. In a computer magazine, she reads that the probability of Outtake hanging in any 15-minute period is 2.5%, while the chance of Outtake and the operating system failing together in a 15-minute period is 1%. Let me just highlight this and word here, because that usually indicates something, right? And so then if Outtake is hanging, what is the probability that the operating system will crash? Okay, so if something has already occurred, what is the probability that the next event will occur? Okay, so that gives you clues here. This question, as you read it, it will give you a clue as to what you're trying to solve. Okay, so let's define our events here. So let A be the event where the Outtake program hangs. And we're going to let B be the event where the system crashes. Okay, so what are we told? Well, we're told that the probability that the Outtake program hanging A was equal to 2.5%, or as a decimal, I can express that as 0.025. Okay. Now, what about this other percentage that they give us, the 1%? So you read this thing carefully. This is the chance of Outtake and the operating system. So this is A for Outtake, and this is B for the operating system. Failing together is 1%. So what we're given actually is not the conditional probability of B given A. It's actually the probability of A and B, and that equals 0.01. And what we're asked to solve is the conditional probability here, so the probability of the system crashing given that the Outtake has been hanging already. So that's what we're trying to solve, which would require a little rearranging of the formula that we had above. So we're going to say here the probability of A and B divided by the probability of A will give us the probability of B given that A has already occurred. Okay. So to calculate that, I just simply plug in my values here. So I have 0.01 divided by 0.025, and the answer to that is 0.4. So here my conclusion is, therefore, the probability, or the chance, that the system will crash given Outtake is hanging is 40%. There's a 40% chance the system will crash given that Outtake has already started to hang or freeze. Okay. All right, let's go to example number 3. So in England, the probability that a day will be both cloudy and rainy is 25%. Both cloudy and rainy. Again, I'm going to just highlight this and here. Okay. Furthermore, 50% of all days are cloudy. Okay. Okay, so determine the probability that it will rain given that it is a cloudy day. So again, these clues in the language of the question. So it would determine the probability that it will rain given that. So given that something has already occurred. What has already occurred? It's a cloudy day has already occurred. So if there's clouds, chances are there might be rain as well. Okay, so how do we calculate this? Well, again, let's define our events. So we're going to let A be the event where we have a cloudy day. And we're going to let B be the event where it's going to rain. Okay, and we're told that the probability that it will be both cloudy and rainy, so A and B, is equal to 25%, so 0.25 as a decimal. And we're also told that the probability of all days being cloudy, well, it's the probability of A, is equal to 50%, so 0.5. So what we're asked to find is the probability that it's going to rain given that it is already cloudy. So the probability of B given that A has occurred. Okay, so that's the big question mark here. So let's solve for it. The probability of B given that A has already occurred is equal to the probability of A and B divided by the probability of A. And that's going to be 0.25 divided by 0.5, and the end result is 0.5. Okay, so therefore, there is a 50% chance for rain given a cloudy day. Okay, so far so good. Let's continue on. Example number 4. So Grace is a kicker on her rugby team. She estimates that her chances of scoring on a penalty kick during a game are 75% when there is no wind, but only 60% on a windy day. If the weather forecast gives a 55% chance of windy weather this afternoon, what is the probability of Grace scoring on a penalty kick in this afternoon's game? A bit more of a trickier problem. So let's start defining by our events. So let's say A is the when we have no wind at all. So that's what we're talking about here. No wind. There's no wind, and let's see the probability to be so what's the other thing? So on a windy day, okay. So on a windy day, so the chances. Let's okay. We have to really be careful here. She estimates that her chances of scoring on a penalty kick during a game are 75% when there's no wind, but only 60% on a windy day. If the weather forecast gives a 55% chance of windy weather this afternoon, what is the probability of Grace scoring on a penalty kick in this afternoon's game? So we're still looking, we're not just doing events of wind and no wind, we have to look at the probability of her scoring. Okay, so I'm going to say event B is her scoring a goal. So I'm going to write here to find the probability of scoring, you must consider the cases of wind and no wind. Okay. So let's look at some probabilities here. So the probability of her scoring, which is B, given that there is given A, so no wind, is equal to 75%. So it's sort of here. So chances of scoring on a penalty kick during a game is 75% when there's no wind. That's important, no wind. So 0.75. The probability of wind, so that's going to be, probability of no wind is going to be what? Well, it says here, if the weather forecast gives a 55% chance of windy weather, then my probability of there being no wind will be 100% minus 55%. So it's going to be 45%. So 100 minus 55% is equal to 45%, or as a decimal, 0.45. Okay. So then what's the probability of her scoring given that there is wind? A prime. So we're now using the complements now. So A prime is when there is wind. So the probability is 60% for her to score if it is a windy day, which is what it says up here. That's going to be 0.6 as a decimal. Okay, so pause there for a moment. Maybe try and absorb that and see if just make sure you really understand what we're looking for. So what we are going to be looking for is the probability of A and B. So the probability of there being no wind and Grace scores, plus the probability that there will be wind, A prime, and that Grace also scores. So that's what the question is. What is the probability of Grace scoring on a penalty kick in this afternoon's game? So we're not even sure if there's wind or not. There's probabilities for each of those cases. If you look at the probability that she will score, and given that there's wind, and probability that she will score given that there's no wind. So what we need are, well, the probability of B given that A has occurred times the probability of A plus the probability of B given that A has not occurred times the probability of A prime. A prime I forgot to write down here. So probability of A prime is the probability that there will be wind, which is 0.55. So I'm going to write that down as well. Okay, so if I calculate this out, I have a 75% chance that she will score, given that there's no wind, times the 45% chance that there will be wind, or there will be no wind. Okay, plus the probability that she will score, given that there is wind, which is 0.6, times the probability that there will be wind, which is 0.55. And if I multiply those values, I'll get 0.3375 plus 0.33, which is equal to 0.6675, and that's approximately equal to 67%. So we can say overall, therefore, there is a 67% chance that Grace will score. Okay? This is all based on whether there's wind or no wind. It's probabilities for each of those outcomes. So what is the total probability when I add them together? It's 67%. Okay. All right, example number 5. Lars is offering juice samples at a shopping mall. The experimental probability of randomly chosen shopper accepting a sample is 15%. The conditional probability of a customer purchasing juice given that they have tried a sample is 20%. No one purchases juice without trying a sample. If Lars offers 500 people juice samples, how many sales will he make? So 500. So you can only know how many sales you make based on 500 people. You can't make any more than. He can't sell any more than 500 sales because he only offered 500 juice samples, right? Because it says here, no one purchases juice without trying a sample. So they have to try a sample. Let's look at our events first. So we're going to say let A be the event where they are trying a sample. And I'm going to let B be the event where they buy juice. Okay, and we're told that the probability of them trying a sample is equal to 15%, or as a decimal, it would be 0.15. And I'm told the conditional probability, so the probability that they buy juice, which is B, given that they have tried a sample, which is A, is equal to 20%, so 0.2. And we're asked to find the probability of them trying a sample and buying a juice. So probability of A and B. So using the formula, it will be probability of B given A times the probability of A. and multiplying those together, 0.2 times 0.15 gives us a value of 0.03, 3%. So 3% chance that probability that they'll try a sample and buy a juice. How does that translate into how many sales he's going to make? Well, if you take 3% of 500, or 500 people that will have a sample, it would be a good estimate as to how many people he will actually sell juice to. Okay, so that's going to be 0.03 as a decimal times 500, and that's going to equal 15 people. So therefore, Lars will make 15 sales. And that ends our lesson on dependent events. And that's the end of our chapter.